So why using EEG as a signal for tracking brain electrical activity and not, for instance, functional MRI, which is absolutely correct approach as well. But there are two aspects that they are distinguishing the two modalities. With functional MRI, we see very detailed images that are mostly static because they are evolving very slowly during MRI acquisition, while with EEG we have a very high spatial temporal resolution, so we can track in few seconds many informations. And beside the fact that in a research lab in a university, having an MRI is not an obvious thing because it's quite expensive. However, the application that I'm discussing today starts from a need, a practical need, which is also in common to what we do at the Institute. Many times we take into account concrete problems, and then we create science from it, but always from a demand. Though the demand here was postural control during the sailing in seafarers in the North Atlantic. High rate of accident, postural instability, seasickness after a few weeks of sailing. Okay, well, how we can measure that? How we can compensate postural instability and decrease accident on board? And from there, we needed to, of course, senti, si è congelato il coso qui. Sorry. So we needed, of course, studying postural control and adding biosignals, adding some measurement issue, to move from the state of the art. So normally postural control is measured with postural stability using a force platform. So you use a force platform that measures the center of pressure. So while you apply a certain stimulus, like stimulators on the calf muscles that you see over there, then the subject moves on the platform and draw let's say, a pattern. And through this pattern, you can detect what is habituation and adaptation. So what is the immediate response to a postural control stimulus and what follows up as a predicted strategy to a stimulus that you expect to happen. So we wanted to study that first. And we added to the normal vestibular research tools the high-density EEG. To make the story short, what we found out is that because reading EEG signal is the real challenge, okay? And I'm always doing the same example. Reading EEG signal is like trying to hear what is happening into the next room. Okay, and in the next room, we have more chance to understand what is happening if we know the story. If they are speaking about history, if they are speaking about geography, if they discuss about muscles, then by hearing the conversation, we can reconstruct narrative. So the same is with EEG. We need to know, we need to engage the brain with something that we expect a response. So evoked potential, and then we read what is happening in the brain. So we did that, and what we realized that to understand the brain electrical response, we need to have a visual stimulus. So when the eyes are open and are looking at something, the brain electrical activity is more visible, can be more read. Okay, that was the lesson that we learned in these first paradigms. So then we create a second paradigm, which is still postural control, but it gives a very strong visual impulses through virtual reality. So virtual reality, high density EEG, and again, a moving platform that synchronized with the visual impulses and create the activity on a boat. So here we have a simulation of a boat in the North Atlantic, and then the subject accommodate the stimulus you see there in the monitor. And while we do and we run this stimulation, we measure brain, heart, muscle, and of course the center of pressure. Now we have been doing this for a few years, and we have collected over 500 acquisitions from mostly healthy individuals, measuring their motion sickness score and measuring their postural control response through the biosignals. I wanted to point out that the paradigms starts with, of course, a resting state. So every time you do EEG, you always wanted to see how a person behaves when has open eyes and closed eyes without doing anything. Right, that's the baseline. But then we give them a static visual stimulus. So nothing is happening except they have open eyes and they look at these scenarios. Then we start the simulation, and they begin by looking at an environment that moves, but nothing else is moving. So the platform is not moving. Immediately after the moving scenarios, it's accommodated and synchronized with the platform. So then they see and they feel. This stimulus increase over time until it's stopped brutally. And then they start to continue to see the stimulus, but there is not movement. So in this way, we have a big chance to understand and predict what is happening in the brain. So we have done this now for a few years, and we have correlated postural control and biosignal with motion sickness. We have correlated postural control and biosignal with concussion, mostly related to sport concussion. And we are studying also early stage Parkinson. Well, we have work on all those type of subcohorts, but I wanted to focus on the recent work we have done on early stage Parkinson, because that's is the directions that is quite intriguing and can be really useful in evaluation for neurodegenerative disease. So what we do and what we have been studying are the differences between early stage Parkinson. And when I say early stage Parkinson, I mean people that they just received diagnosis of early stage Parkinson, of Parkinson disease. So they might be at a different stage when they get the diagnosis from the neurologist, but they are early stage because they just got to know their diagnosis. And what we see, for example, by looking at the postural control, at the stabilography, so the equivalent ellipse that is drawn by the sway. So when you sway, you draw a pattern, and then you can assimilate that, you can model the pattern with an ellipse. And what you see here is that when they only see the moving, but they are not moving at the beginning of the experiment, the patterns for healthy individuals and Parkinson remain unchanged. Okay, so it's very similar. So this way with this, drawing the same pattern. But when you have the same identical stimulus, but after a movement, so you have the movement and then brutally you stop the platform, but you continue to see the visual stimulus. So identical in the beginning, but is a latent visualization of the stimulus. Then you see the difference, and you see that let's say the protection of the Parkinson patient makes them to sway a lot less. So they have a protective reaction. So they obviously contract, and they stay, they draw a pattern that is a lot smaller than healthy. We find also that the muscles that are mostly involved, and they can distinguish pretty much healthy from Parkinson, is the soleus muscle. So the soleus shows more evidence of differences between the two cohorts. And here is the changes, the difference between healthy and Parkinson in heart rate variability during the experiment, from the baseline up to the maximum intensity of the let's way, and until the end of the experiment. So there is a Parkinson in general, they have more, let's say, stress. They are more stressed while they are doing the experiment. Now, I need to give you, for the latest part of the presentation, two pieces of information in order to understand what is happening in the results. So there are, let's imagine, let's see that the following slides, this talk about brain connectivity. So about the activity of the brain along the different areas of the brain. So it's a way to develop electrical activity from EEG. But how electrical activity, by meaning of connectivity, can be modeled? The first, we need to define what are the resting state network. So the resting state network are basically functions of the brain that are localized in a very precise area of the brain. They are both appearing during functional MRI, but also during EEG. So are the same areas that you can see while you are doing functional MRI and while you are doing resting state EEG. So meaning the person has open eyes, but is not doing any specific task. And these areas are, these networks are default mode networks, dorsal attention network, salience network that is more, has to do with what we do, how we process information, motor network, auditory network, and visual network. They are all the main functions of the brain, and they have specific areas of activation. The second piece of information is the brain connectivity. Now, all these areas, they interact to each other, and they interact to each other differently depending what we are doing. Okay, so we have those areas, but these areas, they talk to each other. Okay, we want to understand how they talk to each other during postural control task and between Parkinson and healthy individual. So this is what is happening over 200 individuals that are healthy and during our experiment. So during our experiment, and this is a little bit fast forward, so it's a little bit more faster than is normally in our experiment, but you can see that the equivalent brain electrical activity, so the interactions between the different brain network states, can be modeled over 200 individuals. And this is the way the transaction between the states is happening in our experiment. So you see now there is a movement. The movement goes over 50%. The brain network state did not change in this transaction, but is now changing when it goes at the maximum level. And then you nota bene what is happening now that the brain network state changes while now the platform will stop. So in this last transaction, we see the habituation. So meaning that the postural control has taken, a kind of predictive strategy. So knows that is happening, what is happening. But still, something else has happened after the movement finished, and then probably you didn't notice, but the subject continues to sway even though there is no movement taking over. So now the same approach and the same work, it's done with Parkinson. This is just imagined as a decoration. It serves me to tell from where this information comes from. So you have an EEG, then you project the electrical activity on an anatomical map. You divide the brain in different segments. You assign the different electrical activity that correlates between all those segments. In this case, there were 52 segments of the brain, so a matrix of 52 times 52. And then we see what is happening here. Then from here, then we put together the most significant results and we extract the more significant brain network state. And from there, we can visualize the connections between the areas of the brain. It's almost there. So the brain network states that we extracted from our analysis comparing 20 early stage Parkinson and 22 healthy matched cohort individuals shows that we have the same number of brain network states, but let's say the quantity and the weight of each state during the different tasks is different from each other. So mostly we see that the brain network state number 2 is the one that changes the most during the experiment. But how we can visualize that and how that is related to the resting network state, so it's related to what is happening in the different region of the brain, then you have to translate these results into a graphic theory. So you have to design the different nodes and the different links between the area. And then here you see the different weight of the resting state networks. And yeah, to make, let's say, the story, let's say, concrete and giving you a hint of what we have found out, we are basically showing that there are quantitative index that can distinguish pretty well early stage Parkinson from healthy individuals by using this methodology. Of course, this methodology and the postural control task is nothing that you can imagine into a clinical setup tomorrow. So what we are working on is to resize those paradigms in something that can be used in a clinical setup. So with this, thank you for the attention, and I'm happy to answer questions.